Hello everyone, today I'm talking about curvilinear motion in Cartesian coordinate system. The softball and the car both undergo curvilinear motion. A particle moving along a curve other than a straight line is a curvilinear motion. This curved path could follow 2D plane or could be three-dimensional. For the curvilinear motion, we start from basic rectangular position motion, but we learn other coordinate system later. Okay, put this curve path in x, y, z three-dimensional rectangular coordinate system, and at a certain time, the particle reached to this position. Again, this position can represent by vector r, that we can written in Cartesian vector form as r equal xi plus yj plus zk. And don't forget the position as a function of time. After sometimes delta t, the particle moves to the new position p prime, which can represented by vector r prime. That this change can be shown by delta r. And velocity is the change of position over the changing time and become instantaneously velocity when time approach to zero and become delta r over delta t. Note that if delta t is very small, r and r prime are on the same line. This is very small dr that is perpendicular to the position vector, and we can say it's a tangent to the path. The important conclusion this part, the instantaneous velocity is always tangent to the curve of the path. When position vector of particle p is given by its rectangular component, the velocity is dr over dt, and r is equal xi plus yj plus zk in the rectangular system. So we can write v equal dx dti plus dy dtj plus dz dtk, or x dot I plus y dot j plus z dot k. Dot is the specific for time derivative. Also, we can write the velocity vector as a velocity component, where here vxi, vyj, and vzk represented the velocity of particle in x, y, and z direction respectively. And again, the velocity always as a tangent to the path at any point. Similarly, for acceleration is defined as a dv over dt, or the second time derivative of the position. Acceleration is equal dv x dti plus dv y dtj plus dv z dtk, or x double dot I, y double dot j, z double dot z. And generally, x double dot, y double dot, and z double dot are specific for second time derivative. Also, we can be written in Cartesian form as a axi plus ayj plus azk, that ax and ay and az as an acceleration component along x, y, and z direction respectively. Unlike the velocity, acceleration is not tangent or perpendicular to the curve of the path. Okay. Consider v as a velocity of a particle at time t. After time t plus delta t, the new velocity is v prime, which can be represented by vector v prime. That this change can be shown by delta v. and acceleration is the change of velocity over the changing time, and become instantaneous acceleration when time approach to zero and become dv over dt. Pay attention. In general, the acceleration vector is not tangent to the particle path and velocity vector. Before to see any example, just quick review from calculus course. Derivative of vector function. Let Pu be a vector function of scalar variable u. Derivative of vector sum is dp plus q over du equal dp du dq du. And derivative of product of scalar and vector function dfp over du equal df du p plus fdp du. And derivative of scalar product and vector product for scalar dp dot q du equal dp du dot q plus p dot dq du, and dp cross q du equal dp du cross q plus p cross dq du. We use this rule for the future example and other problems. Okay, let's see this example. During a test flight, a helicopter starts from rest at time 0 and moves in x and y plane. If the acceleration during the interval time from 0 to 10 seconds is ax equals 0.6 t and ay equal 1.8 minus 0.36 t, what is the magnitude of the helicopter's velocity at time 6 seconds? Okay, we have analyzed the motion in each coordinate direction independently. Integrate each component of the acceleration to determine each component of the velocity as a function of time. Integrate the x component of the acceleration to determine the x component of the velocity as a function of time. Evaluate the x component of the velocity at time 6 seconds and integrate the y component of the acceleration to determine the y component of the velocity as a function of time. Evaluate the y component of the velocity at time equals 6 seconds. Calculate them, and finally calculate the magnitude of the velocity at time in 6 seconds. And the V total equal 11.6 meters per second. Let's look at another example. Okay. An object travels from the origin along a curved path as shown. If its horizon velocity Vx equal 80 meters per second and t as a second, determine the magnitude of its velocity, acceleration, and distance from the origin at time 2 seconds. Okay. The curve that objects follows is given. The vertical position y at any given time is related to horizontal position x by the equation equal 1/4 times x3 and half power. Also, the horizontal velocity vx as a function of time, also given vx equal 8 times c. And they ask us to find the magnitude of velocity, acceleration, and distance from the origin at time equal to seconds. So, since Vx equal dx over dt, we can use the Vx function to find the horizontal position x as a function of time. Vx equal 8t. Through simple integration x equal 4t squared. And y is related to the x through y equal 1/4 times x3 to the half power. Therefore, y, the vertical position as a function of time, is equal to t to the third power. Therefore, the position vector is r equal xi plus yj equal 4t2i plus 2t3j. And from differentiation, v equal dr over dt. The velocity vector is 8ti plus 622g. And differentiation again, acceleration equal dv over dt and equal 8i plus 12tj. Therefore, for at time 2 seconds, we can evaluate position vector, velocity vector, and acceleration vector. And now we know that how to represent the vector from static. Also, how to calculate the magnitude of vectors. This is our result. Okay, this is extra question. You have to answer it. Thank you.